Well, thank you for bringing me up, and I think I consider this up because I'm certainly at a higher altitude than I was back there in Louisville. It is Louisville. That's right. It's spelled Louisville, but it's pronounced Louisville by local folk. What I want to talk about first is about floating forest theory. But I want to broaden it a little bit. I made it into a talk which focuses on, it tells you a little bit of how the theory was developed in the first place and something of the success of a theory and an example of a successful creationist theory. The initial challenge to me a number of years ago, actually in 1989 when I'd just finished my doctorate, and while I'm doing my formal education, I wasn't paying much attention to the arguments that were being made against creation or that. My formal education was in geology and paleontology, and my first area of expertise in graduate school was macroevolutionary theory. So I was trained in those disciplines and trained with the evidence that they present, and so didn't really have much chance to rethink these things until I finished my doctorate. When I did, in the summer, in between then and starting my job at Bryan College, where I taught for 17 years, following that, I took the 7, what I thought were strongest arguments for evolution, and sat down and said, now, how would I understand these things from a creationist perspective? And I satisfied myself in just a few months there that the 7 largest arguments could be easily subsumed within creationism, and that there was no further need for concern in those areas. Most of that stuff is still not published, but one of those claims, one of the 7 that I thought was most significant, was the claim that the fossil order is explained by evolution, and that the fossil order is thus evidence for evolution. Now, putting this a different way, what this statement means, I think I'm in the way standing here, is organisms are appearing in a particular order in the fossil record, which is the order you would predict if evolution brought organisms into the fossil record, into existence. So the very first thing is, when you see such a concern, such a claim, you first need to determine whether the claim is true or not. Most claims turn out to be unsubstantiatable. They're not actually correct claims. So the first thing you need to do before you worry about trying to explain it is make sure it really is a truism. So how do we do this? Well, first of all, we need to determine the evolutionary order. Now, what I'm going to do here is I'm going to focus on plants. There's a reason for this. When I first did this, I did it for everything. When I did it for everything, I found that there wasn't much order to explain. There was really only 2 groups where there was any order that corresponded between the fossil record and an evolutionary theory, and that would be the order of first appearance of plants, the major groups of plants, the equivalent of what would be phyla in animals. They're called divisions in plants, in the plant world, and then there would be the vertebrates, the appearance of the vertebrates sequence. And so I'm going to focus on this because it has interest. At that point, I deduced that 95% of the fossil record has no correspondence between evolution and the order in the fossil record. So there's really nothing to explain. At a 5% confidence interval in statistics, we would say there is no order to explain, period. Let's go home. But nonetheless, the 5% that remained was interesting. The 5% were those 2 groups, the plants and the vertebrates. And here I want to focus on the plants. And here's an evolutionary tree of the plants built from studying only the biology of the plants and making assumptions that are typical in evolutionary theory, which is that when you have similarities, 2 organisms that are more similar, we're going to assume that they're more closely related. And in this process, we develop an evolutionary tree, a tree of characters coming into existence through evolutionary time. And then now what we can do is, from this tree, we can deduce what the expected evolutionary order would be of these tree groups. For example, the very first branch down there at the bottom is going to be the first thing you would predict. So the Horneophytopsida should be the first thing you expect in evolutionary theory. Then Aglaophyton, and then Rhiniopsida, and Zostrophyllopsida, and so on. This is how you build the ranking of these things. So now we have a list of the plant groups and an order, a rank order for them. Now we want to compare that with the order in the fossil record. So now we have to look at the fossil record of those creatures. And so here, taking time from the left to the right, it's usually, of course, going up in the fossil sequence. The lowermost fossils are all the way over to the left. The uppermost fossils are to the right. And I'm only taking it to the Permian. I'm only considering the primary, or what some people call the Paleozoic fossil plants. For my purposes here, that's all I'm interested in. And this is a diversity curve. So that, like, for example, the Phyllocopsida, the ferns, you see a height, that first line is above the bottom. That is proportional to the number of genera, and 50 is over there, so we've got about 50 genera of ferns at any given point in the fossil record. So the diversity increases and pretty much stays constant for the upper part of the Paleozoic. The Lycopsids are a very large group in the Paleozoic. They arise early in the Paleozoic, come to maximum diversity at 275 million years before present conventional dating, and then drop to the end of the Permian, and so on. So this is a diversity curve, and it also tells you when the first appearance of each of these groups would be, and that's what we're interested in. So the first plant in the fossil record at all is a member of the Horneophytopsida. In fact, they very quickly go out extinct in the fossil record soon thereafter. And then the second, and the third, and the fourth, and the fifth, and the sixth, and so on. From this, we then deduce a sequence of first appearances of the major groups. Then those ranks can be placed in there. Now we have a way to compare the predictions of evolutionary theory with, in fact, the expectations or the observations in the fossil record. You can plot them too, plot one versus another. The red line would be the 45-degree line, perfect prediction of the fossil record from evolution. The points are very close to that line. The R in a Spearman rank correlation test is 0.994. It's very good. It's a very good order sequence, and we've got a number of organisms in the sequence. So the reliability of this is very high, which means the divisions of plants, the major groups of plants, are coming in an evolutionary order. They're appearing in the fossil record in the order evolution would predict. Very powerful, spectacular sort of order. Now, at this point, an evolutionist, of course, would quit right here. There's no need to go any further because the case is finished. But of course, my perspective is different. I don't believe that evolution brought the plants into being in that sequence. So the sequence now becomes intriguing to me. Now I want to know what the sequence means in terms of creation. So whereas the evolutionary sequence would be satisfactory explanation to an evolutionist, it's not to me. So I'm wondering if there isn't another way to explain the sequence. So what's the order like? Going back to the very same data that was used to build the evolutionary tree, we now look at what that data, how they built that data, and what conclusions they derive from it. First of all, if you look in a paleobiology textbook, you'll learn that the evolutionary story on the plants, basically the simple story, is an evolution from algae to land plants. It's an evolution from plants that live entirely within water to plants that will ultimately live independent of water. It's a story of increasing terrestriality. It's a story of also increasing your height above the substrate, because you're floating around in water, you're not above the water level. But when you get onto land, you have the ability to grow tall. So it's also a story of increased height. above the substrate. You go from early plants here that actually produce eggs and sperm that swim in the water to meet each other, to at the other end of the spectrum, something like a corn plant, where the sperm and the egg never contact the outside air, never have to swim through water or anything else. It's completely independent of standing water. So you have complete dependence on standing water at one end, independence of standing water at the other. That's the basic story, the evolutionary story of the origin of the plants. And if you look at the actual data, the similarities that group the groups together. So why do you separate the Horneophotopsida from the rest of them? There's a particular character there at 3b, which is